This topic today is section 7.7 in your textbook, and it's on inverse relations and functions. And I want to use this first slide as a way to introduce today's lesson and kind of give you a taste for what we're going to be doing in the slides to follow. So what I've done here is I'm illustrating a relation. The technical definition for relation is a set of ordered pairs. And so what I've done here is I've created a relation called A. And A is this set of ordered pairs. It's in table format. It's provided here in this blue table. And then just another way of representing A using set notation is here in the red. So really no difference other than just the way it's presented. So that's a relation. Here's my set of ordered pairs. I want to introduce you or refresh your memory as to what this notation here in the context of this little -1 exponent that's being used. It looks like a -1 exponent, but it really refers to the notation that says the inverse of. In this case, it says the inverse of A. So let me show you how easy it is when you're given a set of ordered pairs to write the inverse of a relation. Very simply, it involves looking at the ordered pairs and switching places with the xy coordinates. So if relation A had the point 6, -1, the inverse of A would have -1, 6. And that would be true for all of the ordered pairs. You would just go down the line, and when you switch places with the xy coordinates, that represents the inverse of the relation. Okay? So that's a pretty easy thing to understand, I think. If you want to find the inverse of a relation, if it's given in a set of ordered pairs, you just switch places within each pair with the xy coordinates. Okay, well, let's just move on then, build on this way of thinking. Problems 6 through 12, that's really where you're going to start in this assignment. The directions in the book say to find the inverse of each function. And then we'll do that first, and then I want to come back to this question: is the inverse a function? Well, before we were given a set of ordered pairs, and we said, well, that's pretty simple. You just take each ordered pair and switch places with the xy coordinate. Well, we don't have a set of xy coordinates here, but we do have the actual x and y variables. So to find the inverse of a function, like number 1, as you can see here, I'm giving you a two-step process. The first thing you will do is switch places with the x, y variables. So you can tell here, I just rewrote this equation, but I've switched places with x and y. So that takes care of step number 1. And then step number 2, solving for y, will be just what our normal routine is. We need to isolate y. So the first step in getting that accomplished will be to add 7 to both sides. And then my final step will be to divide by 4. That's the way we undo multiplication by 4. So my answer here to the first part of the instructions, find the inverse, and I'll just turn it around. The inverse will be y equals x plus 7 divided by 4. Okay, so that's the answer to the first sentence. We'll call that maybe answer part 1. Well, now, what is the answer to this question? Is the inverse a function? In class, I kind of went through an elaborate description using graphs, but I think I'll cut this a little bit short. I'm just going to put it to you this way. If you are given the equation of a linear function, which is what the red represents, it's a linear function, has a y-intercept of -7 and a slope of 4. Well, I hope you can tell that the inverse is also a linear function. I mean, maybe it'll look more familiar if we wrote it out as y equals 1/4 x plus 7/4, which means we have a y-intercept of 1 3/4, and from there we would count a slope of 1/4, which would be a line that has a positive slope, so it would do something like this. And this line, if we put it to the vertical line test, would pass, because if we draw a single vertical line, we're only going to touch the graph in one point with a single vertical line. So the answer to the question for if you're given a linear function with which to find the inverse, then the answer to the question, is the inverse a function, will always be yes. As long as we're dealing with a line that has a non-zero slope, then the answer, you can bank on it, it's always going to be true. The answer to the question will be yes, the inverse is a function. Well, let's take a look at number 2. Number 2 is not linear, it's quadratic. And another thing is it's given in function notation, whereas number 1 is given in what we would call equation form. And some people have asked me in the past, well, how can I switch places with x and y when there is no y? Well, most people understand that you could rewrite this equation function as y equals 3x squared plus 2. And some people choose to do that just so that they can see that x and y now can be switched. That needs to be the first thing to do, switch places with x and y. And now go about the routine for solving for y. And that's going to mean subtracting 2 from both sides first. Then we're going to divide by 3 on both sides. And then hopefully you remember that in order to solve for y, to undo raising y to the second, we will do the square root. And another very important thing to remember, when you do an even numbered root on both sides of an equation like we are here, square root, we have to include plus minus as part of our answer. So the answer to the first sentence, finding the inverse, it will be y equals plus minus the square root of x minus 2 over 3. All of that fraction underneath the radical. Okay, so we've taken care of the first sentence. Now we have to answer the question, just like we did for linear. Notice the answer to the question for the linear equation that we're given was yes, the inverse is a function. But what about quadratics? And the short answer is going to be this. Without getting into an elaborate graph, if we did graph this given function, it would look something like this. It's a parabola that opens up. It's 2 units up above the origin, up the y-axis. So that's a rough sketch. Well, the inverse of this is, it's like taking this parabola that opens up, if we were to graph it, and it lays on its side opening to the right. Okay, so if we did take the time, and in just a little bit we will be doing some graphing. You don't have to graph on 6 through 12. But if we did take the time to graph, our original function, 3x squared plus 2, would look like this if we graphed its inverse. And hopefully you can tell that this graph does not pass the vertical line test. With a single vertical line, I'm hitting 2 different points on the graph. So, bottom line, when you're dealing with quadratics and you're finding the inverse function, and you're asked to determine if the inverse is a function, the answer to that question for quadratics will always be no. And I hope this little picture helps you understand why. For quadratics, the inverse will always be either a parabola opening to the right or if it's flipped from upside down, then it would open to the left. But in either case, neither of those will pass the vertical line test. Okay, so to answer your question that the book is going to ask, for linear equations for which you're finding the inverse, as long as the slope is not 0, the inverse will always be a function. For quadratics, the inverse will never be a function. Okay, so let me circle, here's our answer part 1, and then answer part 2 is no. Okay, when you get to 14 through 22 even, you're going to be asked to graph a given relation and its inverse. Okay, so this shouldn't be too bad. Let's start by graphing y equals 3x minus 10. That has a y-intercept of negative 10. There's negative 10 on the y-axis, and it has a slope of positive 3. Up 3 and right 1. 3 right 1 again. I need to get my toolbar to show. Give me just a second. Because I want to be able to draw some straight lines. All right. Okay, so let's see. Here is the graph of the equation y equals 3x minus 10. All right, so graphing the inverse from this is really a pretty simple process, because if you'll go back to my first slide, I said that if you have a relation, which is just a set of ordered pairs, then to find the inverse, you just switch the xy coordinates. Well, this is a relation. It is a set of ordered pairs. Now, granted, it's an infinite set of ordered pairs, but all we need are a few of the ordered pairs, and we have 3 of them identified here as points. So here's how I'm going to come up with the graph of the inverse. This is 0, negative 10 on the original. So the inverse will contain the point negative 10, 0. Okay, let me just write that so you can see it. On the original blue, we had the point 0, negative 10. So if we want to graph the inverse, we just switch those, switch places. This is what I was doing on that first slide. All right, let's do another one. On the blue graph, we have the point 1, negative 7. So that means to graph the inverse, I'm just going to switch places with those, and I'm going to do negative 7, 1. Okay, let's try one more. Here I notice the point 2, negative 4. And so for my inverse, I'm just going to switch places with those coordinates and do negative 4, 2. And when I draw the red line, that will represent the inverse graph for y equals 3x minus 10. So that would be a way that you're going to answer. Let me do this. Finish it off. And you don't have to do these ordered pairs on your graph. I just did that so hopefully to show you how you come up with the points for the inverse. Okay, so that would be a typical answer for the 14 to 22 even problem. So let's try this one. We worked on this one in class. Hopefully you recognize it's quadratic, so it's going to be a U shape. I also hope you recognize that this is vertex form. We haven't talked about vertex form since first semester. So let me give you again, just to refresh your memory, what vertex form looks like and why we call it vertex form in the first place. All right, using variables, so I should put the variable a here. Using variables, this is vertex form, and the reason why we call it vertex form is the h, whatever number is in this h location, is the x-coordinate of the vertex. So vertex form makes it very easy for us to locate the vertex of the parabola. The h number is the x-coordinate, so applying that to this problem, the x-coordinate of the vertex will be 3. The y-coordinate comes from a number outside the parentheses, either added or subtracted, and since there is no number, then it's just 0. So the vertex of this parabola is going to be the point 3, 0. And it's going to open up because the a number, which is understood to be 1, is positive. Okay, and now I'm just going to do some inputs using numbers around my AOS, which is x equals 3. Let's input 2 for x. Okay, what do we get as an output if we input 2? Well, 2 minus 3 is negative 1, and negative 1 squared is positive 1. Okay, and because of symmetry, that makes it nice to just easily plot another point on the other side of our line of symmetry. All right, and let's just keep building from there. What about an input of 1? 1 minus 3 is negative 2, and negative 2 squared is 4. So here's the point 1, 4, and here's my symmetry line, so I can put another point there, and let's draw the U shape, or parabola. Okay, the directions say to graph the relation, that's what we just did, and its inverse. So let's just take these 5 points that we plotted and switch places with the xy coordinates, and we'll plot those. So 3, 0 is on the red, that means 0, 3 will be on the inverse. 2, 1 is on the red, so 1, 2 is on the inverse. 1, 4 on the red, so 4, 1 on the inverse. Let's see, this point is 5, 4 on the red, so 4, 5 will be on the inverse. And let's see, 1, 2, 3, 4, 1 is on the red, so 1, 1, 2, 3, 4 is on the inverse. So those 5 blue dots, let me connect them, represent the graph of the inverse. Okay, and so that would be a typical answer for the problems 14 through 22 even. Okay, I think I'll skip over this one. When you get down to problems for you, it's just evens. Problems 24 through 28 even. This will wrap up your notes, but I'm going to change the book directions just a little bit. All I want you to do is, basically you're not going to have to worry about finding the domain and range of f or the inverse of f. I just want you to find the inverse and then tell whether or not the inverse is a function. Okay, so I'll do number 23 as an example. Again, it's just basically practicing what we've already done. Finding the inverse, if you want to, you can think of this as y equals 3x plus 4. So we'll switch places with x and y. And then we'll solve for y. Subtract 4. Divide by 3. And this equation represents the inverse. Now what I could have done, since this was originally in function notation, probably better to show it like this. Remember that little -1 exponent in this context says the inverse of f is x minus 4 over 3. Okay, so I've done this. I found the inverse, and now I'm going to determine whether the inverse is a function. Well, I showed you earlier, if you're starting off dealing with a linear function that has a non-zero slope, then the inverse of that will always be a function. So the answer is very simply yes. If, and I don't have another one to do. Yeah, I do. I've got one. So we'll do another example of a quadratic. So this would be your answer, for example, for number 23. So here's number 25. Let's take a look. This is a square root. So we're supposed to find the inverse. Once again, I'm just going to write it in y equals form. Okay, well, how do we undo the square root of x plus 7? Well, from our previous lesson, we raise that to the second power. And if I do that to the right side, I must also do it to the left. All right, and now how do I solve for y? Oh, I'm sorry. Let me back up. I didn't switch places with x and y. I apologize. Okay, I'll go back. You probably caught that, didn't you? Okay. Now we're going to raise both sides to the second power. Okay, and now to solve for y, it's pretty simple. We just subtract 7 from both sides. And this represents our inverse, which would be better shown as this. All right, so now my question is this a function? Well, notice I wasn't handed originally a quadratic. This isn't raised to the second power, it's actually raised to the 1/2 power. So if you were to graph this, you should have a basic understanding of what this graph would look like. It's a parabola that opens upward. Okay, so rough sketch, it's a parabola that's moved 7 places down on the y-axis. You don't have to graph it, but just to give you an idea of why our answer is what it is, does this graph represent a function? Does it pass the vertical line test? And the answer is yes, it does. And so to answer the is the inverse a function part, the answer would be yes. Okay? I think that's all I have as far as examples, and your assignment is there. So work on these and come and see me in academic support, or you can send me an email if you have any questions.